Static equilibrium, tension force. There is a whole field of problems in engineering and physics called statics that has to do with cases where no acceleration occurs and objects remain at rest. Anytime we construct bridges, buildings, or houses, we want them to remain stationary, which is only possible if there is no acceleration or no net force. There are two types of motion that we need to consider, and in both cases, motion is to be prevented. What are they? The two types of static equilibrium relate to linear, or translational, and rotational acceleration. Linear acceleration would be when the object or components of the object is moving in a straight line, and rotational acceleration is when it pivots about a point and rotates. Neither works well in a building or a bridge, or a house. In order to prevent acceleration, that is movement, for the first case, the net force is equal to 0. And in the second case, the net torque is 0. Only the linear acceleration will be covered in this section. Rotational equilibrium is covered in the rotational motion chapter. Previous problems involved a rope supporting an object by exerting a vertical force straight upwards along the same axis as the force mg that was pulling it down. That led to the simplest case, that if the box is moving up or down with a constant velocity, then A sub y is 0 and the tension force, Ft, is equal to mg. There was also the case where an applied force acted on one object but not the other. A tension force acted between the two masses. So m2, I'll draw it up here, there's more room. m2 is pulling m1 in this direction with the tension force. And because of Newton's third law, we have an action-reaction pair here, and m2 is being pulled to the left by m1. And these forces are equal. They are tension forces. The applied force acts only on m2. Mechanical forces, like the applied force and tension, have to be connected to the object they act on. And we're having one rope here, and then we'll assume this is a different rope. So there's no connection, physical connection between m1 and the applied force. So when I complete my free body diagram, at least in the x direction, we're not going to worry about y right now, F is not acting on tension. So let's just summarize that. Since the rope is not connected to m1, it does not act on m1. The mechanical forces, like applied force and tension, have to be connected to the object they act on. A more interesting problem is for two or more ropes to support a stationary object, which means A equals 0 by exerting forces at angles. Since we're going to focus on the tension force for a while, and using additional subscripts 1 and 2, we'll save notation and replace F sub t with t. As a physics person, you're allowed to do this. In this case, since it is rest, the sum of the forces in the x direction and the y direction on the object are 0. Where would you see this outside the physics classroom? And a little note here, the sketch shows the tension, not the lengths in the individual ropes. This is indicating that this force will be greater than this force. We're going to calculate that shortly. You can see this in cables that hold traffic lights over the street. So here's our traffic light, and we'll exaggerate this a little bit. The lines go up. They're not perfectly horizontal. Can you figure out why? Well, let's see. If it was perfectly horizontal, all right, we've got mg going down here. Where's our force in the up direction to counter it? We don't have it. So what happens is the line sags a little bit, so you can have a component of force in this direction and also in the up direction to balance off the mg. Since the only other force on the object is gravity, the vertical components of the force exerted by each rope must add up to mg. And if the object isn't moving, then A sub y is 0. So the sum of the forces in the y direction is t sub 1i plus t sub 2y minus mg equals ma sub y, 0. That is equal to this. And then we put mg on the other side. Now let's work in the x direction. The only forces in the x direction are those that are provided by the x components of t1 and t2. Again, the object is not moving, it's in static equilibrium, so A sub x is 0. So the sum of the forces is minus t1x we're going to assume that direction is negative, plus t2x equals ma sub x, which equals 0, minus t1x plus t2x equals 0, and then we show this. t1x is equal to t2x. And once again, t1x has a negative sign, such it is pointing to the left. Going forward now, we will be dealing with the magnitudes of the various tension components. We take into account the directions in the below equations right here, where t sub 1x was assigned a negative value as it was pointing to the left, and t sub 2x, t sub 1y, and t sub 2y were all assigned positive values. That's the great value of making a sketch and a free body diagram. You don't have to worry about angles greater than 90 degrees and the different signs of the cosine and sine functions in the various graph quadrants. T1 and T2 will now be resolved along the x and y axes. mg is already just in the negative y direction, so we're okay there. So over here, we make T1 and T2 a little lighter as we replace them with their components. Theta this time will be the angle between the vectors T1 and T2 and the y-axis. So let me look at T2x here. That's pointing off to the right. And there's T2y. And the same thing for T1, just going in the other direction. Be careful of how the problem is stated. Sometimes the angles alpha 1 and alpha 2 are given. Those are the angles that the ropes make with the support platform. The ceiling, for example. They might give you those. They're complementary to the angles theta that are used here. And here's our problem. Calculate the tension in the two ropes, T1 and T2, if T1 is at an angle of 50 degrees from the vertical, and the second, T2, is an angle at 20 degrees from the vertical, and they are supporting an 8 kilogram mass. Use theta 1 and theta 2, and assume 2 sig figs for each angle. Resolve T1 into its x and y components. So sine of theta 1, and here's theta, is going to be opposite over hypotenuse. The opposite is T1x over here, and the hypotenuse is T1. So T1x is equal to T1 sine theta 1. Now, if we had used alpha over here, in that case, T1x would have been T1 cosine theta 1. But we're not. We're using theta. So you always have to look at your triangle before you decide what trig function. Now, what's the next one? Cosine theta 1 is equal to adjacent over hypotenuse. In this case, the adjacent side is T1y. The hypotenuse is still T1. So we have T1y equals T1 cosine theta 1. Now resolve T2 into its x and y components. Similar process, and we find that T2y is T2 cosine theta 2, and T2x is T2 sine theta 2. Take the resolved vectors, which is right here. We've done that on the past few slides. The given values, we'll substitute them in to that, and then we put them into Newton's two laws here, one for the y direction and one for the x direction. And then we will solve the simultaneous equations, also known as system of equations. After I go through this, you may want to pause it and see where all the math is, just to make sure you understand it. So here's where we do all the substitutions. T1x is T1 sine theta 1, which is T1 times the sine of 50 degrees, which is 0.77 T1. Then T1y, T1 cosine theta 1, we substitute that and get 0.64 T1. Then we keep going with T2x and T2y, get those values. And finally mg, it's going to be 8 kilograms times 9.8 meters per second squared, and we get 78. The signs are already taken into account with the following two equations, so just substitute in the above values, the magnitudes. Once again, that's the advantage of a free body diagram and not worrying about the signs of the sine and cosine functions. So here's our T1y plus T2y equals mg. That fits in over here. and then T1x equals T2x, we just put that like this. So that all came from the upper left-hand corner. From the previous slide, we now have two simultaneous equations with two variables. That's good. That means we can solve them. So we're going to solve equation 2 for T1 and then substitute that T1 into equation 1 and solve for T2. So T1 is equal to 0.34 over 0.77 T2 or 0.44 T2. We then plug that value. Let's see, how do I want to show this? We'll take the 0.44 T2 and put it in over there. So we have 0.64 times 0.44 T2 plus 0.94 T2, and that equals 78. So T2 is 64 newtons. Now substitute T2 into equation 2 and solve for T1. And we get T1 is equal to 28 newtons. Earlier it was indicated that T2 is greater than T1. The calculations confirm this. T2 is greater than T1, which means that it is picking up a greater load. A way to determine this without the mathematics is to note that T2 is more vertical than T1. So if two people are trying to lift a load, the stronger person should take the more vertical rope. Also, the sum of the magnitudes of T1 and T2 are greater than the weight of the box. But we only take the y components for our free body diagram, so everything works out. Take a limiting case where θ1 equals θ2 equals θ. That means the ropes make equal angles with the vertical, so our T1x and T2x wind up being T1 sine θ and T2 sine θ. Now, we already know T1x has to equal T2x for the block not to move, or whatever else you're suspending there. So this now turns into T1 is equal to T2 equals T. Right? So we cross that out. We showed that that's equal over here. So each rope has the same tension. The load is shared equally. Now examine the forces in the y direction. Once again, theta will be the same. So T1y is T cosine theta, and T2y is T cosine theta. Substitute that into this equation, and we have T cosine theta plus T cosine theta equals mg. Do a little bit of algebra, and the tension is equal to mg over 2 cosine theta. That's the tension in each wire, or rope. Let's take a limiting case again. Physicists love doing this. What happens as the support wires get more horizontal? For example, they start going like this, and then like this, and like this. What happens as theta approaches 90 degrees? Remember, we're measuring theta from the vertical axis. As theta approaches 90 degrees, the ropes become more horizontal. The tension required to support the box approaches infinity. Can you think of an example of this effect? And you can't use the traffic light one again. Electrical power transmission lines. And hopefully how you can see it's a bit of a bend here. This helps explain why the lines sag. The force required to maintain a horizontal position would exceed the strength of the lines. And external wires are wrapped around them to add more support, and also the sag gives you another force in the up direction to hold them from falling down.